and good evening. I hope you will be okay. Mrs. Rasha, I think she wanted to speak. I enabled your microphone. You can speak now. I don't have any voice from you, Mrs. Rasha. You can speak now.
Salam, Doctor.
Hello?
Can you hear me good?
Excuse me, Mrs. Rasha, you have both system and mobile. Please disable one of them.
Yes. Now? It's good?
Yes, it's okay.
Thank you. Doctor, please, can you give us some example about the transport daily?
About?
Can you give us some example about the transport daily and delta daily?
Okay. About transport delay.
Delay and delta delay. Sorry.
Okay.
Thank you so much.
You're welcome. Okay, let me then start by replying to your question from this session and giving you some example about the transport delay and delta delay. The first one is transport delay. As I told you, a delay between two lines, for example. Okay. As you can see, we have three kinds of delays in digital systems and in Vhdl. Okay, we have three kinds of delay. As I told you, we have the first one is inertial delay. Second one is transport delay. And the third one is delta delay. And you know that inertial delay is really the delay of the gates, of digital gates. For example, AND, OR, XOR, and etc. But what about the transport delay? As I told you, the transport delay is a delay transport delay. Is a delay between data lines. For example, we have a clock, or we have a data bus. This is really a line from 2 point A to B, for example. And we know that here we don't have, okay, let me to, one of the students wanted me to repeat the explanation of the delay. I started the explanation and I told you that we have 3 kinds of delay in Vhdl modeling. The first one is inertial delay, the second one is transport delay, and third one is delta delay. Okay, we'll start by, I think I told you about the inertial delay, and now in this session, salam. And now in this session where I want to speak, or I want to take you some examples about the transport delay and delta delay. The transport delay, let me to write it for you. The transport delay is a delay between points from a data line, from a clock, by a clock, or by a data bus or buses. A delay in data lines or clock. For example, here we have a line, and this line started by point A and ended with point B. Okay, we will have a delay between point A to B. We say this transport delay. We must know that here between A and B we don't have any transistors, we don't have any gates, we don't have anything. Really, we only have a line, a wire. This wire, because of the capacitance and resistance effects, has a delay. And we must consider this delay. We call this delay transport delay. And we have an estimation amount from a delay. For example, we know that a delay between A and B is, for example, 50 nanoseconds. For example, we write like this: E between A and B. This is the delay between A and B is 50 nanoseconds. This means that if we have any changes from 0 to 1, from 1 to 0, and other things, this change will be appear at B after 50 nanoseconds. How can we write this? For example, we write like that: E is, and we must write like this. Let me to change the color. Transport B is A after 50 nanoseconds, like this. Then B is A after 50 nanoseconds. And a keyword like transport, it means that this delay is from transport delay. Then if we have any change in A, we will see this in B after 50 nanoseconds. Like that. Let me to write it. For example, Okay, you can see that this is the waveform for point A. For example, we can see the changes in some special times. For example, 7 nanoseconds, and here we have this at, for example, 15 nanoseconds. Okay, we can see all of these changes after 50 nanoseconds at point B. For example, I want to write point B. What about point B? Like this. And this will be the waveform of point B. Is it right? Do you understand? Yes. 50 plus 7 and 50 plus 15. Do you understand? Okay, Mrs. Rasha, okay. Mace, okay. Other students, Muhammad, okay. Muslim, okay. Yasser, okay. Marve, Habib, Noor, Ahmad, Muhammad Nasr, okay, very good. Okay. And now, let me take you or give you other example about very good, okay, very good. To take you another example about another delay model, delta. As I told you, delta delay model is a special technique that Vhdl editor is used for management of order in Vhdl simulation. Okay, very good. Thank you. For example, let me come back to the slide. As you can see here, in this system, we know that if input 1 or input 2 will have changes, these changes will propagate to other nodes. For example, if input 2 have changes, this change will be propagated to S2 and S3 at first. And in other steps, these changes will be propagated to S4 and Z at second step. Okay, then let me go to the next slide. As you can see here, input 2 has a change, and this change propagated at the first step to S2 and S3, as you can see. And after this, at second step, this change will be propagated to Z. Then if we can say these steps as delta seconds, we can see that after delta seconds, S2 and S3 will be changed. And after 2 delta seconds, Z or output will be changed. But when we want to see the result, the simulation result, all deltas will be limited to 0. Then we can see all changes at one time, 10 nanoseconds. Then this is a hidden technique. This is an internal technique that only Vhdl editor is used. We don't see this. We don't see anything about delta. We don't need to see anything about delta. We only see the result. But this is, as I told you, an internal technique that the Vhdl editor is used to save or to maintain the order or to manage the order of nodes and to manage the order of changes from input to output. This is the only example that we can speak about it. We can see other examples like this. For example, let me to have an example like this. Okay, this is a one gate, input 1 and not gate, inverter gate. Consider a chain of this gate, for example, like this. Okay, we can see that input 1 and now here W1, this is the first node, W2, let me to consider S1, it is better. S1, S2, S3, S5, and this is the output S6, for example. You can see that we have some nodes here, and we don't have any delay for the gates. But if we have any change in input number 1, how can we see the other changes in S1, S2, S3, S4, S5, and S6? For example, we have a change here like this. 0 at first, and then 1. Like this. Okay, for example, this change, it happened on 10 nanoseconds. We have another changes in S1, S2, S3, S4, S6, and S5 and S6 in other seconds. And what about them? We know that in S1 we will have this change at 10 nanoseconds plus delta nanoseconds, and in S2 we will have this change in 10 nanoseconds plus 2 delta nanoseconds. In S3, 10 nanoseconds plus 3 delta. In S4, 10 nanoseconds plus 4 delta. In S5, 10 nanoseconds plus 5 delta. And in S6, 10 nanoseconds plus 6 delta. Then you can see that we have a propagation. Yes, really, this is right. But when we want to see the final simulation, okay, when we want to see the final waveform, all delta will be limited to 0. Then we have another result. What about the final result? Yes, it means that all of them, S1, S2, S3, S4, S5, and S6, all of them, S1, 2, 3, 4, 5, 6, all of them will be happened on 10 nanoseconds because delta is limited to 0. And 1 delta, 2 delta, 3 delta, all of them will be limited to 0. Okay. Do you understand? Okay, very good, very good. Mrs. Rasha, do you understand? Yes, okay. You're welcome. Okay, now let me to speak about other things Okay, very good. And I think I explained you the slides up to number 7. I told you about data types, and I told you about let me to use them, Vhdl number 6 and Vhdl number 8. Okay. جلسه ششم. You mean that I didn't told you about the data types? Vhdl data types. This example type, my logic type, my logic vector type, state, and something like this. No? Okay, okay. Okay, okay. No problem. Okay, I will start this. Let me only some minutes to use from my flash. مشکلی نیست باشه. خب اما okay. Now we want to speak about data types in Vhdl. We have two kinds of data types in Vhdl. The first one is about predefined data types in Vhdl, and the second one is about the user-defined data types in Vhdl. This is the first one, predefined data types in Vhdl, and this is the second one, user-defined data type in Vhdl, or the data types that can be used by the user. Okay, at first, let me to speak about data types. What about data types? For example, you write A to point in, I mean input, bit vector, bit, this bit vector, this bit, a standard logic vector, and etc. All of them are data types. then when you write like this, for example, you write the Vhdl code like this. A input it. Split is data type. This is the data type. And now we want to speak about this data type. We can have different data types. What about these data types? As you can see, we have different data types, and the names of them are like this. These data types are defined, some of them are defined in Vhdl editor, and some of them are defined in IEEE library for Vhdl. For example, bit and bit vector are defined in Vhdl editor. A standard logic and a standard logic vector are defined in IEEE library. A standard U-logic and a standard U-logic vector are defined in IEEE library. Boolean, integer, natural, real, all of them can be defined in Vhdl editor. Signed and unsigned, both of them are defined in IEEE library. Okay, and what about them? What about the explanation of them? You know that bit and bit vector have only 0 and 1 for their values, and this data type can be synthesizable. I mean, it can be implemented on FPGA. The other one is a standard logic and a standard logic vector. This data type has different values: 0, 1, high impedance or Z, and other values H, L, don't care, undefined, and etc. But only the values 0, 1, and high impedance can be synthesizable, and the others are not synthesizable. And a standard U-logic and a standard U-logic vector, what about them? They are the same as STD logic or a standard logic. The only thing is that we add this U. It is the abbreviation of unresolved. I explained for you about resolved and unresolved signals. This is an unresolved signal because if the user wanted to define an unresolved signal, and if the user wanted to define table assignment, the user can use from STDU logic and STDU logic vector. But this situation is rarely happened for you. In many times, in usual times, you as a user uses from STD logic and STD logic vector. The other type is Boolean. Boolean has two values, true and false. And if we can map this true and false to 0 and 1, it can be synthesizable. The other is integer. It is really the integer numbers, positive and negative numbers. If the range of this number is limited, they can be synthesizable. The other is natural. What about the natural? I mean natural numbers and 0. If the range of using them is limited, it can be synthesizable. The other is real numbers. Real numbers, you know about the real numbers. But real numbers are not synthesizable. at all. They can't be synthesizable. And the last one, or the last data type, is signed and unsigned numbers. It is really like a steady logic vector, but it is a special data type that by using a special IEEE library, the arithmetic operations are defined for them. But this is for old days. Nowadays, we can use from a special library, IEEE library, and use arithmetic operations for steady logic vector. Do you understand? Okay. Very good. Okay, no problem. Let me send it for you now. Students, all of you are joined in this group, System Boomerang, or not? Okay, you can use it now. If there is any student that is not joined to this group, it is better for that student to join to this group. Please, one of the students take the link of this group for other students that join to this group. Mm. صدا خیلی بده. یکی از دانشجویان نوشته صدا بد است. Okay. And now we can go to other slide. Slide number. And now we want to speak about the user-defined data types. Data types, or some data types that can be defined by the user. What about them? As you can see, these data types, or user-defined data types, we have two ways of defining. This is the first one, and this is the second one. One of them defining a specific range of numbers. For example, type my integer is range keyword is range from -32 to +32. This is a special define of data type. After this, we can write like this: signal, example, for example, signal S1 and S2 as my integer. This is the user-defined data type. I define my integer as a new data type, and I use it for defining S1 and S2. We have two signals, S1 and S2, and both of them are my integer. Okay? Another defining, for example, defining enumerated numbers. Type state is, and the values S0, S1, S2, S3. These are some values. The values are optional. You specify the values. For example, we specify S0, S1, S2, and S3, for example. And after this, we can write like this: signal, for example, A and B, state. It means that A and B are two signals, and A and B can have these values S0, S1, S2, or S3. For example, I can write like this: A is S0, for example, or B is S, for example, 3. You understand? Okay. Okay, very good. And another example here. Type my logic is, and the values 0, 1, high impedance, undefined. 0, 1, Z, X. Okay, and another example, and another type. Type my logic vector. It is a new type, my logic vector. And we can write like this: type my logic vector is array. Is array of my logic. My logic vector is array of my logic. What about the range of this array? The range of this array is here, natural range. Then this range is optional range. The user can define the range. The user can specify the range. Okay? Is that right? And now we can write some examples. For example, here signal for example W1 and W2 are my logic. They are 1-bit number. Then here W1 can be 0 or 1 or Z or X, like that. But another example here is another signal. For example Z, or for example W is my logic vector, and we can specify the range of my logic vector. For example, 3 down to 0. In this situation, for example, W can be, for example, 0 0 0 0, can be 1 1 1 1, can be 0 1 ZX. This is 4-bit number. Okay? Do you understand this? Okay. Another students, do you understand? 1 2 3. Only 3 students. 4 5 6 7 8 9. Only 9 students. It is not so good. The other students, okay, very good. And now the other example is a special example. Let me to write it here. We can go here. Type my array is array of a standard logic vector 7 down to 0. And what about the dimension of the array from 0 to 3? Then in this data type, we define a special data type. We define array from some special numbers. It is an array of a state logic vector. This is the state logic vector. A state logic vector from 7 down to 0. Then it is 8-bit number. 8-bit number here. This is 8-bit number. But we define an array from these numbers, and the dimension of this array is from 0 to 3. It means that we have 0, number 1, number 2, and at the end number 3. Okay. Signal X as my array. Signal X is my array. It means that, for example, we define a signal with number X. And this is my array. The data type is my array. Then we have, for example, x0. x0 is the 0 element of the array. x1 is the first element of the array. x2 is the second element of the array. And x3 is the last element of the array. And all of them are 8-bit numbers. Do you understand? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Only 10 or 11 students, I think, are really online, and the others are, I think, offline. Okay, and after this, in another slide, as you can see, the first one is some speaking about signed and unsigned numbers. As I told you, in previous days, in old days, signed and unsigned number are used, but nowadays we can use from our special IEEE library. Special IEEE library, STD logic signed and STD logic unsigned. By using these special libraries, we can use arithmetic operations for STD logic vector data type, and we can use arithmetic operations for them. Then we can not to use from signed and unsigned data types. This is the first one. The other one is we have some special and useful functions in IEEE libraries that can change or convert some data types to the others. For example, here you can see this. this instruction. What about this? Y is conv integer p. What does it mean? P here is a standard logic vector. For example, 8-bit number, 16-bit number. This function convert p to an integer number. Get p and convert it to an integer number. For example, plus 100. For example, minus 50. And something like that. And save it into y. Y is an integer number. We have some little amount of these functions. 1 or 2 or 3 only functions that convert one data type, one number from special data type to another. And using them can be useful for you because it can help you to easily change one data type to another in your Vhdl coding. Do you understand? One of the students of Mrs. Rasha writes that if we don't have vector, then how? If you may have 1-bit number, for example, std logic, you may have vector std logic vector. You can define some other vectors like my array, as I told you in previous slide. Here, my array is a vector of std logic vector. This is really a two-dimensional vector, but in this situation, we only have std logic vectors. I mean, for example, here, in this situation, we can write only x0, x1, x2, or x3. Maybe you say that, for example, we want to write x, 3, 4. For example, you mean the 4th bit of x3, it is not acceptable, it is not true, it is false. Okay? This special writing is not true, it is false. You can only write x0, x1, x2, and x3. Do you understand, Mrs. Rasha? Because we can't write two-dimensional array index in Vhdl. We can write only one-dimensional array index. Okay, and the last one. Speaking about the Vhdl data types is ended up to now. And now we want to speak about Vhdl operators. Mrs. Rasha, do you have any question? Okay, I uploaded the record of this second in session number 6 and 7, I think, or 7. No problem. But if you have any other question, you can send your question directly by WhatsApp. Okay? Please, I think the voice for her is cut off. Then you please, I think by somehow send my speaking to her to know that. No problem. If you have any question, you can send it directly by WhatsApp for me. Let me write this. Okay. And now we want to speak about Vhdl operators. We have some special operators like assignment operators, logical operators, arithmetic operators, comparative operators, shift operators, and concatenation operators. These operators are used for different operations like arithmetic operations, logic operations, and etc. But what about them? What are the symbols of them? As you can see, for concatenation operator, we have only one operator, and I explain it for you. This operator, for example, if we write like this, for example, W is A B. It means that it gets A and B as 2-bit, for example, numbers, and connected these two numbers to each other and create a new special number, for example, with name W. If A and B, both of them are 1-bit number, W will be 2-bit number. We call this concatenation operator. Another operator is shift operators. These shift operators are used to shift data, for example, to right or to left. Shift right and shift left, for example. They can shift only 1 bit to left or right. The other operators are comparative operators. They are used for comparing two numbers. They are especially used in conditions. For example, if then else conditions, switch case conditions. For example, conditional assignment conditions, and something like that. For comparing two numbers, we can use from equality, non-equality, less than, greater than, less than equal, greater and equal, or equal. They are comparative operators. The other thing after comparative operators, the other thing is arithmetic operators. Arithmetic operators are used for arithmetic operation. We have different arithmetic operators. Plus for addition, minus for subtraction, star for multiplication, and all of them in this line are synthesizable. Then addition, multiplication, and subtraction are synthesizable. But the other arithmetic operators like division, here, power, this 2 star is power, absolute of number, mod and rem. Mod and rem are used for division. If we divide two numbers with each other, the residue of division is rem. And the result of division is mod. Okay? Then mod and rem, absolute, division, and power. All of them are not synthesizable. They are synthesizable in some special cases. Okay? Students, if my voice is okay or not. Because the students, some of the students write that voice is not good. Okay. I think the internet connection, the connection status is not good for some specialists. For some students, maybe the internet line, maybe the time, other things is not good, I think. Okay. After arithmetic operators, we can go to logic operators. All logic operations in Vhdl are synthesizable. They can be implemented on FPGA. And all of them are not any symbol. They don't have any symbol. We must type them. Not, and, or, NAND, NOR, XOR, XNOR. You can see that. All of them are typing. And assignment operators, as you can see, you see up to now one of them here, this assignment operator. But we have another assignment operators, and I will speak about them in other sessions and in offline classes. Do you understand? Okay. Okay, very good. And now we can go to Vhdl number 7. Vhdl number 7 is really very easy because in this Vhdl we speak about the software. For example, we have two software for this course. One software is for, let me to write it in Paint. have two software for this course, or we can have two softwares for Vhdl modeling. Really, in Vhdl working, we have two steps. In first step, we write Vhdl model, writing Vhdl code or Vhdl model, and we compile this. And then we simulate this. Up to now, we picked the Vhdl code, but we have another step. In this second step, we must have a synthesis step. We really have a synthesis. In synthesis, we check Vhdl code for FPGA implementation. And the first one is synthesis. Another one is implementation. In implementation, we really implement the Vhdl code into FPGA. Implementation can have some other steps like place and route. In place and route, we exactly specify the FPGA cells that are used for implementation. Okay, we can have a software for all of these steps, or we can have a software for only first step. I give you two software. If there is any student in Iran, please come to my office and get me the software. I have the software. I have two software for Vhdl modeling. The software is Vhdl. The software is Active Vhdl. For only Vhdl modeling, Active Vhdl. I have two versions of this, version 8 and version 9, 8.3 and 9.2. And I have another software, but I'm not sure that I have this now. I must check it. I have another software that can support all of the steps. This another software is ISE. And this software ISE Xilinx from Xilinx company. But ISE from Xilinx company is free for download. You can download it. If you can have a good internet connection, because I think in Iraq it is better than here, because you can easily go to Xilinx site and sign up for Xilinx and get the software. It is free for all users. You can download it very, very easy. Then the other software is ISE Xilinx. I must check it. If I check it, I think I have this version, this software, but I think I have an older version of this software. For example, version number 14, I think. But if you check in the site, you can find some newer versions of ISE Xilinx. Okay, this is the software. And we start by ActiveHDL, because ActiveHDL is simple and it can help you for VHDL coding. Okay. And VHDL number 7, it is not really a slide. It is really speaking about software. Then I speak about it in offline classes. Unfortunately, it is in Persian. Speaking about the software is in Persian. Now I want to make another file for this for the VHDL in English, to speak about the software in English. I think I can prepare it in 2 or 3 days later, and then I will upload it in your class. Do you understand? Okay. Inshallah, after 2 or 3 days, I will upload it in your class. Okay, then the next session, we must start by VHDL number 8. Okay. Okay. Inshallah. If there is any question, please write it for me. Okay, Khuda Hafiz. Is there any student that have question? Please write it for me. I will stop the sharing of the desktop. to all of you. One of the students typed for me that she has some questions. You can write it for me, or you can write it by chat for me. If you want, I can enable your microphone. You can raise hand, enable raise hand, and I can enable your microphone. سلام بفرمایید.
وقتتون بخیر.
متشکرم.
ببخشید جلسه پنجم سلاید پنجم. بله. استدی لوجیک وکتور 1
توی جلسه پنجم استدی لوجیک وکتور 1 و 0 بوده.
جلسه پنجم سلاید 5.
نگاه کنم. خب من یه شیر اسکرین بزنم. خب این که نه هیچی. این
بله دکتر استدی لوجیک وکتور 1 down to 0.
بیام اینجا. کدوم یکیش؟ اینجا. این اینجا. بله خب این چیه؟ آره 1 down to 0. نگاه کن ببینید اینجا دیکودر. آره اینجا دیکودر دو. بگین به من بگین. one down to 0. آها خیلی خوب نگاه کنین اینجا دیکودر دو تا ورودی داشته X و Y. ما اومدیم یک سیگنال میانی تعریف کردیم به نام W که 2 بیتی هست. چون 2 بیتیه به همین خاطر تعریف شده 1 down to 0. 1 down to 0 یعنی چی؟ من اینجا یه پینت درست کنم. 1 down to 0 یعنی چی؟ اینجوری. خب اینم از این. خب 1 down to 0 یعنی چی؟ این که W هست 1ش اینه 0ش هم اینه یعنی 2 بیتی. W یعنی 2 بیتی هست. درست شد؟ حالا اینجا Y و X کانکتنیت شده به هم چسبیده شده یه عدد 2 بیتی و اون عدد 2 بیتی توی W ذخیره شده. این قسمت این شده Y. این هم شده چی؟ X. اینها هر کدوم یک بیتی هم کلش میشه 2 بیتی و توی W ذخیره شده. متوجه شدید؟
بله خیلی متشکرم.
وایسین انگلیسی هم بگم برای بچه ها. Students. One of the students asked me why we write here signal W is a logic vector down to 1 down to 0. 1 down to 0 means 2-bit number. But why we define a 2-bit number? We know that we have two inputs here, X and Y. We get these two 1-bit numbers, Y and X, and concatenate them. Concatenate means that we connected with each other and save them into 2-bit number, like here. We get at first, we get Y and we get X separately and connected with each other and change them to a 2-bit number. This new 2-bit number is W. This is the cause of defining W. And 1 down to 0, it means 2-bit number. 1 index for 1, second index for 0. This is index for 1 bit. This is index for 0, 2 bits. Do you understand? بله بفرمایید.
ببخشید سوال دیگر. ممنونم. جلسه چهارم اسلاید 28.
خب
بله دکتر این
خب
این دوتا
چی شده دوباره به من بگین مشکلش چیه؟
S1 جلسه
اسلاید 28
28
اجازه بده. اینجا. Okay. Okay, no problem. It is a little mistake. This mistake is like this. Let me to check it for you. This is really S1 and this is really S0. Okay?
لا دكتور يعني in S0 S2 تمام؟
Yes. Really this is true. This figure is true. Okay? Do you understand? This figure is true.
يعني دكتور in 0 يعني أول 0 دوم يك 0 يك.
Yes, like this. Like this. For example, 0 0 0 1 1 0 1 1. Okay? Another question?
يعني إن جاء يعني not logic فقط 0 1
No. And means, for example, When we write like this, when we write S1 is 0 and S0 is 0, we mean 0, 0 condition. It means that both of the inputs must be 0. It is 0, 0 condition. It is 0, 1 condition. It is 1, 0 condition, and it is 1, 1 condition. Okay? This AND means that both of the conditions must be right, must be true. Okay?
اوکی دکتر خیلی ممنون تمام شده.
خواهش میکنم موفق باشید. خواهش میکنم. Is there any other question for students? Okay, then I hope you will be okay and you have good times. Thank you very much for participating in class, and goodbye. خدا حافظ.